Welcome everyone to Quantum Computing from Zero to Hero with Amazon Braket. I'm Jackie Ko, Professional Services Cloud Architect. My first love academically was mathematics. I went into university to study physics and graduated in mathematics and computer science. These are all loves of my academic life. Out of all my nerdy interests, I've been fascinated with quantum mechanics, the science about the world of the very tinies, atoms, electrons, photons alike. I wrote my first quantum program in 2017 to verify some ideas in physics. I was hooked ever since. I started to share my study notes online and write articles about quantum computing on LinkedIn. After Amazon Braket was announced in reInvent 2019, I participated in the Amazon Braket GA process, helping the new service to become generally available. Today, I'm taking you through a journey of quantum computing. I will answer some common questions. Where are we at with quantum computing and where are we heading? What is a quantum computer and why do they run fast? What does the quantum computing language look like? I will also share my personal experience on how to start learning quantum computing. Let's begin. Where are we at with quantum computing? Let's first trace back to where we have been. Epic moments in the history of computing are marked by famous quotes. Here are some of them. Can machine think? Alan Turing developed the code-breaking machine Colossus as portrayed in the movie The Imitation Game. This is a question he asked in his paper Computing Machinery and Intelligence in 1950. The number of transistors and resistors on a chip doubles every 24 months. The Moore's law has been upheld for over half a century, and now we can put almost 140 million transistors, or 5.5 times the Australian population, into 1 square millimeter. We will probably reach the physical limit of transistor density in this decade. About 40 years ago, Richard Feynman has suggested a model of tiny computers obeying quantum mechanical laws, which is what we call quantum computers now. Peter Shor has devised a quantum algorithm in 1995 that can factorize large integers, effectively breaking RSA encryption, but we are yet to have a quantum computer powerful enough to run his code-breaking algorithm yet. When Nature magazine interviewed Peter Shor in 2020, he talked about replacing RSA with a secure post-quantum crypto system. He said, "I think it's something we know how to do. It's just not clear that we'll do it in time." A new technology is like fine wine. It takes time to mature. Is it the right time to bottle the quantum wine? Is it the right time to lift ourselves from zero to hero? I believe it is. We are seeing more competing quantum technologies appearing like mushrooms after the rain. For example, D-Wave Systems' quantum annealing technology, IonQ's trapped ion technology, and Rigetti Computing's superconducting technology. These quantum technologies can be accessed using Amazon Braket, a fully managed quantum computing service that helps researchers and developers get started with quantum computing. Amazon Braket democratizes quantum computing and brings various quantum technologies to everyone under a single framework. Many commercial use cases of quantum computing are being explored, including machine learning, physics and chemistries in material science and medicine, optimization in logistics and operations, and the list goes on. Customers are seeing potentials in the industries such as financial services, automotive, energy and gas, pharmaceutical, biotechnology, manufacturing, academic research, and the public sector, to name a few. And Amazon is here to innovate for you and with you. You may become a thought leader by starting your quantum computing journey now, because anything you do may become the world's first. It could be a quantum application idea, a quantum algorithm that solves a complex issue, or an innovation that kickstarts a trend. If you were late to the party, catching up could be a great challenge, as building the expertise and resources would take time. What we're going to do in this session is to give an introduction to quantum computing so that you can speak the quantum language, start exploring quantum computing, and gets ready for the first wave of the quantum computing revolution. These are the three pillars of Amazon quantum computing ecosystem. Amazon Braket to democratize quantum computing so you can explore and experiment with the quantum technology. Quantum Solutions Lab for you to get expert help in research collaborations. And Center for Quantum Computing to conduct original research on quantum algorithms and hardware. Amazon Braket is a fully managed development environment using Jupyter Notebook or your favorite IDE. You can build, test, and run quantum algorithms, also called quantum circuits, to learn and explore the quantum computing technology. The Amazon Braket Jupyter Notebook is pre-installed with quantum circuit examples, which you can also download from GitHub and have a preview before you sign up with Amazon Braket if you have not already done so. These are the simulators and quantum processing units, or QPUs, that Amazon Braket provides. They are in 3 regions: Northern Virginia, US East 1, Northern California, US West 1, and Oregon, US West 2. These regions are close to the 3 major QPU partners, but you can log into these regions from anywhere in the world to submit quantum tasks. Starting from the left of this architectural diagram, you may submit quantum tasks from your Jupyter Notebook or local IDE to a quantum computer provided by one of our technology partners. Alternatively, you can use a managed simulator. You may also download the Amazon Braket Python SDK and run quantum circuits on a local simulator without logging into AWS. The Amazon Braket Examples GitHub repository has lots of very useful content to help you go from zero to hero. As you see in the diagram, the quantum magic comes from the quantum hardware. What are they, and how do they work differently from classical computers? What is a quantum computer? Quantum computing is the use of quantum phenomena such as superposition and entanglement to perform computation. Classical computers are now everywhere. You're watching this presentation on one, and you probably have one in your pocket or on your wrist as well. They seem to be able to do anything under the sun, but there's a limit. For example, breaking RSA encryption involves factorizing a large integer, a task that would take a classical computer trillions of years to complete. A quantum computer can do it in 10 seconds. But your online bank account is still safe, as quantum technology is still faced with the challenge of noise and scale. Currently, a quantum circuit can run for only a fraction of a second before its quantum bits becomes corrupted, or in quantum speak, decoherent. This is because quantum bits, or qubits, are very sensitive to environmental interference, or noise, like electromagnetic radiation that exists all around us. Also, quantum computers these days have less than 100 qubits, and to break RSA encryption requires over 4,000 qubits. The scale is not there yet. Despite the recent progress on quantum computing technology, having a powerful enough quantum computer for commercial use is still years away. That said, we need to start learning quantum computer now instead of waiting for its maturity, because programming model is very different from what we are used to, and it takes time to learn and retool. For example, with classical computers, the same input gives you the same output under the same condition, while with quantum computers, the outcome is innately probabilistic, even with perfect noiseless qubits. We need to run the same circuit many times or many shots to find the probability distribution of the results and derive the outcome. Another weird thing with quantum programming is that all operations need to be reversible, so no copying and no deleting, as they are prohibited by nature, as described in the no cloning and no deleting theorems. Learning to program without copying and deleting could be fun. With all these differences, quantum computers are not going to replace classical computers. Our strategy is to have the CPU offload complex but short burst computations to a QPU coprocessor. This hybrid model is very promising as we move forward with noisy intermediate-scale quantum computers, or NISQ, N-I-S-Q. Let's illustrate the probabilistic nature of quantum computers by first recalling how classical probability works. If we toss a fair coin, we will have a 50-50 chance of getting a head or a tail. If we toss two fair coins, there are 4 possibilities, each with a 25% chance adding up to 100%. Let's throw 2 coins with some biases. Here we have coin A with a 70-30 head-tail bias and coin B with a 20-80 bias. Now we throw both coins together. You can work out the probability of the 4 results by simple multiplication. 7 times 2 is 14, and therefore we have a 14% chance to get a head-head. 7 times 8 is 56, so 56% chance to get a head-tail. Likewise, 6% a tail-head and 24% a tail-tail, adding up to 100%. If you do not know the biases in advance, you can work backwards by throwing the 2 coins for, say, 1,000 times and get the probability results of the 4 head-tail combinations, then factorize the 4 terms to find the biases of the 2 coins individually. In the quantum world, coin tossing is a little different. If you toss a fair quantum coin, if there's such thing, you still have a 50-50 chance of getting a head or a tail. But when you toss 2 fair quantum coins together, there can be various results depending on how you throw them, or in quantum speak, what quantum circuit you are putting them through. It may result in this. Some magic has put the result to 50% head-head and 50% tail-tail with no other possibilities. This is called a Bell pair. As you see, the probability distribution cannot be given by classical probability multiplication. The 2 coins are now either both heads or both tails. Although they are still random, they are random together. If you measure 1 coin and find a head, the other coin will change to a head instantaneously. This phenomenon is called quantum entanglement. The correlation of the 2 entangled qubits is instantaneous. Even if you separate them far apart, farther than light or any form of signaling has time to reach. There are profound philosophical implications in the physics of entanglement, but we may well leave the arguments to the theorists. We mere mortals just want to program a quantum computer, don't we? We may try the Bell pair program yourself by logging into the Amazon Braket console, create a Jupyter notebook, and find the quantum circuit under the directory Braket examples and subdirectory getting_started. You may challenge yourself by producing a biased measurement result other than 50-50. I'm sure you'll learn a lot about manipulating quantum probability through quantum circuits. You may wonder, qubit cloning is not allowed, but isn't entanglement a kind of cloning? The answer is no. In classical computer, after copying A to B, the 2 data are not correlated moving forward. With quantum entanglement, however, the 2 entangled qubits will correlate even from afar. Measuring A will affect B instantaneously. But mind you, we can't use entanglement for faster-than-light communication, which is prohibited by nature, another no-go called no communication theorem. Now you may think that entanglement is like assignment by reference, which means 2 pointers pointing to the same data. Not really. 2 entangled qubits are still 2 individuals. It's just that their quantum states correlate in a non-classical way. Copying A to B will destroy the original value in B, a process that is irreversible. But an entangled qubit pair can be unentangled and have their original quantum states restored. In fact, all quantum operations must be reversible. You may do so by running the quantum circuit backwards with inverse quantum gates. You can try this on Amazon Braket. In an ideal noiseless quantum world, like the local simulator, with a quantum algorithm, you can always derive the input from the output. Not so for a classical algorithm. Keeping a redundant copy for error correction is straightforward in classical computing. However, you cannot copy a qubit for a backup, So when environmental noise takes away quantum information, qubits become corrupted, a phenomenon called decoherence, which cannot be reversed. A qubit state can be anywhere between 0 and 1, so there are many ways a qubit can go wrong through decoherence. You need probably 1,000 entangled qubits to implement a self-correcting logical qubit. Quantum error correction is an active area of research, as we need to live with noisy quantum computers for maybe a long while before a breakthrough on quantum technology to reduce noise. Why do quantum computers run fast? Here is a question. A quantum computer runs fast because it tries all answers in parallel. Is that true? Throwing 2 coins can give you 4 possible results, but we know that there is only one single reality under your palm, and such reality has already been determined after the throwing. We just don't know which of the 4 possibilities have been realized. Likewise, when 2 unknown random bits are fed into a classical program, only one of the 4 combinations is in the computation, and the result is deterministic. However, in the quantum world, the 4 possibilities are like 4 notes of a musical chord. When the chord is played, you can clearly hear all 4 notes separately. This is the wave-particle duality concept in quantum mechanics. In other words, all 4 possibilities are equally real. If you feed the 2 quantum bits into a quantum circuit, all 4 realities participate in the computation simultaneously, and the result becomes probabilistic. Therefore, you can manipulate qubits using a quantum circuit and do all those wonderful things like augmenting the likelihood of some results and diminishing others, effectively playing the quantum harmony. For example, here is the result of feeding the 2 qubits into the Bell circuit, one of many ways to throw 2 quantum coins. The more I learn about quantum computing, the more similar I find music and quantum computing are. Here is the Cavatina guitar tab that I arranged while I was not doing STEM things. There are 6 strings. The numbers on the strings represent the position of your fingering. You play the music beat by beat from left to right, and hopefully make a beautiful tune. Here is Grover's algorithm for searching. 6 qubits are used in the computation, so you can see 6 horizontal lines. The first 4 qubits encode the result, like a quartet, and the last 2 are ancillary qubits, like accompaniment. The blue boxes and thin wires with circles are quantum gates operating on the qubits, like the guitar fingering. The QPU runs the circuit from left to right step by step, like following a metronome. At the end, you measure the probability results and derive the outcome. Isn't this music to your ears? Let us explore how this new paradigm means in terms of compute power. 2 classical bits can represent 4 mutually exclusive states. The register is in a single state of either 00, 01, 10, or 11. Like in a melody, a single note at a time. 2 quantum bits, however, can represent 4 quantum states simultaneously, which means 00, 01, 10, and 11 at the same time. Like in a musical chord with 4 notes, each has its own character and possibly played by a different musical instrument. They are all real at the same time. If you want to simulate 2 qubits with a classical computer, you need 4 complex numbers to represent the 4 quantum states. If you have 3 qubits, you need 8 complex numbers. 4 qubits would need 16, and so on. For a quantum simulator with 34 qubits, like the Amazon Braket SV1 simulator, we would need 128 GB of memory and a CPU powerful enough to brute force the calculation in such a large scale. There is a global race to create the first quantum computer that even the top classical supercomputer is not powerful enough to simulate. This would be a milestone called quantum advantage. Here is a blog posted by Jeff Barr, VP and Chief Evangelist of AWS, announcing Amazon Braket in 2019. There are 3 parts in it. Let me illustrate each part with a musical analogy. Quantum computers work by manipulating the amplitudes of the state vector. You may take amplitudes of the state vector to be the sound of a musical chord. To program a quantum computer, you figure out how many qubits you need, wire them together into a quantum circuit, and run the circuit. This is like saying to write a song, you work out the notes you need, arrange them with the melody line and chords, and play the song. When you build the circuit, you set it up so that the correct answer is the most probable one, and all the rest are highly improbable. In the same way, you produce music by coming together and playing the instrument to make a beautiful sound. A quantum circuit is to find the solution of a computational problem, while a piece of music is to express and entertain. Although the objectives are different, the way to achieve them are similar, both by executing a prearranged pattern over a period to produce the outcome. Now let's answer the original question. Quantum parallelism does not mean that multiple computations are happening in parallel universes. You have 4 soloists playing their parts in isolation is not a quartet. The 4 of them need to come together physically, entangle with each other emotionally, superposition their parts to harmonize, then beautiful music will come out of the quartet. To take the musical analogy further, we have been playing solo music with classical computers for over half a century. All we have been hearing is a single melody line played by a single musical instrument. In the new paradigm of quantum computing, for the first time, we hear a symphony with a multi-part harmony. It is a completely different experience. Now let's see how to compose a quantum symphony. What does the quantum computing language look like? Amazon bracket is named after the bracket notation devised by English physicist Paul Dirac, who first represented quantum states and quantum operations using this notation in 1939. As you see in the title, bra and ket are 2 different mathematical constructs. The ket symbol on the right represents a quantum state. You don't need the bra symbol to begin with until you dive deeper into the quantum technology. Let's revisit the 2 biased coins. Classically, we represent the probability distribution with an equation of simple multiplication. The quantum language to describe the same probability distribution is not very different. You just need to add some glitter. Number 1, we put the quantum state in a ket. Number 2, we put a square root sign on the probability and call it the amplitude. So the absolute square of the amplitude is the probability. And number 3, we use a circle with a cross in it to indicate a special kind of quantum multiplication called outer product or tensor product. For now, you can take all these as a formality. You may choose to dive deeper into the mathematics of linear algebra, but it is not required to get started with quantum computing. Recall that the 4 quantum states are like 4 notes of a musical chord with individual amplitudes. You wouldn't want to draw musical chords everywhere in your study notes, so you use a column vector like this. What does the bracket notation mean physically? Here is how we express a superposition with the bracket notation. Recall that superposition is like multiple musical notes played at the same time. When a qubit is in a state of 0 and 1 with a 50-50 chance, we write this. With the left-hand side and the right-hand side of the equation are equivalent. The expression on the left-hand side is easier to write and used more often, but when you do quantum gate matrix calculations, the vector form on the right-hand side is more convenient. There are no fixed rules. Remember to absolute square the amplitude to get the probability. Here, take the absolute value of 1 over root 2 and square it. The result equals to half, which means 50% chance for each quantum state 0 and 1. Here's the 2 qubit scenario. Their 4 joint states are being considered together. Now our musical chord has 4 notes. In quantum speak, the outer product joins the 2 quantum states, so we can consider their probability properties together. You can expand the first expression into the second one in orange in the same way you do with traditional multiplication. The probability of each quantum state is a quarter, which is 1 over 2 absolute squared. I keep saying absolute values because amplitudes are complex numbers. They can be negative or imaginary, as long as their absolute squares sum up to 1, a condition called normalization. Quantum operations that preserve the normalization condition are called unitary operations. As you dive deeper into the Amazon bracket examples in the Jupyter Notebook, you may find yourself playing around with the mathematics more often. Then you know you are on the right track to become a quantum hero. Now we have covered the fundamentals and notations of quantum computing. You may use this slide as a reference to start exploring quantum computing using Amazon Braket. I would like to recommend you starting with this notebook on your way to become a quantum computing hero. Feel free to take a screenshot and use it as a starting point of your quantum journey. How did I start mine? I started by creating something and breaking it. As Richard Feynman said, "What I cannot create, I do not understand." This is especially true if you self-teach when there's no external enforcement. Getting excited about things I create and seeing how they work are my main motivations to learn. Let's learn like a child. They are relaxed and empty by nature. They articulate and do without fear. The acronyms of READ may help. Relax. The fear of getting things wrong is a big hurdle for learning. To me, it's more fun to learn by getting it wrong and working out the right way than to have someone telling you up front. And ironically, you'll learn faster and keep what you learn for longer by exploring along a long and winding road than by being led to the destination in one go. Go out and play and break something. Relax and enjoy. Empty. Throw away what you know. Some quantum computing concepts may be counterintuitive, like superposition and entanglement. You may just take nature as she is and manipulate qubits using quantum gates in the way the physics and mathematics tell you. Articulate. Like speaking a language, you don't need to know the entire dictionary to say hello world. Likewise, you don't need to understand all aspects of quantum computing to start talking and building. Create your first Amazon Braket notebook, write some simple quantum code, and start speaking the quantum language. Share your experience and knowledge with your team and community. Do. Try well-known algorithms, manipulate them and see how they behave. Ask yourself how and how come. Experimentally verify your ideas. If you get stuck, try something new. It may inspire you for a breakthrough. The above is my way of learning quantum computing that happens to work for me. I hope they are useful to you too. There are some useful resources I'm sharing here about learning and building quantum circuits. I included the 2 Amazon Braket GitHub links in case you missed them in previous slides. You joined the AWS Summit to learn, and you can keep the learning going after the summit with resources from AWS training and certification. We offer over 65 courses, many available free and on demand, as well as virtual and instructor-led training. AWS experts will help you or your team learn to apply AWS services to your business, unlocking new insights and value. When you're ready, prepare for the AWS certification exam, which validates your skills and provides an industry-recognized credential. For more information, visit aws.com/training and be sure to check out our AWS Ramp-Up Guide to learn more. Your feedback is important for us to improve. Please complete the session survey. Thank you for watching Quantum Computing from Zero to Hero with Amazon Braket.